Okay, so we've been talking about chapter three here, which is bonding. Um, we've obviously talked about previously the sort of three types of bonds: ionic bond, nonpolar covalent bond, and polar covalent bond. We talked about the use of electronegativity to help us determine, really what type of bonding that we are sort of dealing with. Remember that if you use the sort of values, goes from 0 to 4, 4 being the most electronegative, 0 being not so much. If you have a difference of 0 to zero point 0.4, again, you have a nonpolar bond, which essentially means it's considered that we have equal sharing of electrons within that bond between the two atoms. If you have between above zero point 0.4 to below 2, again, we have some unequal sharing of electrons, and that would be more of a polar covalent bond. And obviously, again, as we talked about a number of times, approximately above 2, usually in most cases, you're dealing with an ionic bond. And we talked about the idea that, you don't really necessarily need the numbers for an ionic bond as long as you can recognize it as a metal and a non-metal. And obviously our general trend for electronegativity can help you determine if a bond's going to be polar or non-polar, especially if you're dealing with two elements that are within the same either period or the same group. You can just use the general trend and really determine the polarity of the bond. Remember that we then talked about sort of drawing Lewis structures. And when we draw Lewis structures, there's several steps that you want to kind of follow when you draw a Lewis structure. And we did it last time, but basically, some important points of that was you really want to sort of figure out the logical sort of arrangement of how all the atoms sort of come together. Again, to help you decide what should perhaps go in the center, the least electronegative atom is usually the one that occupies the center position. Um, Things like hydrogen, which obviously can only have two electrons, should never be in the center. Otherwise, obviously, it will have more than two electrons. Fluorine, which is the most electronegative, typically doesn't find itself in the center. But a lot of times, what we have is a center atom, and everything is directly attached to that center atom. Not 100% of the time. Again, we saw that with something like nitric acid, where there actually can be multiple sort of center atoms. So it is possible to have structures where you do have sort of more than one center atom. But in a lot of things that we do draw sort of in this class, it does revolve around kind of one center atom usually, and other things attached to it. Once you sort of have the arrangement, really the most important thing when you're drawing a Lewis structure is to calculate the total number of valence electrons. Again, we could go to the periodic table and use the group numbers to help us calculate that really quickly. The group number does equal the valence electrons. So once you figure out the total number of valence electrons, that's really important because that's the exact number of electrons that your picture has to have. I can't have one electron more or one electron less. It's got to hit that right on the nose. Once you have the total number of electrons, you got the logical arrangement. Really, the sort of process that you want to follow is you want to take a single bond from the center atom to all the outside atoms. You want to figure out how many electrons you just used when you did that. Then you want to take the remaining electrons, and they should be added to the outside atoms in pairs. So not individually added, but again, as dots, non-bonding electrons on the outside atoms in pairs, until you pretty much fill up all the outside atoms with 8 electrons. Unless, of course, obviously you have hydrogen on the outside, then it would get no dots. If you filled up everybody on the outside and you still have electrons still to put on your picture, then you go to the center atom, and that you fill up obviously with dots as well, so paired electron as well. Now, once you're all said and done and you sort of placed all of your electrons onto your picture, the last thing that you really want to do is make sure that you have met the octet rule. Again, R2 for hydrogen. It is at that point really that if you have not met the octet rule, then you want to basically try to fix that situation by making a double bond. You may have multiple options where you can make a double bond, but you can choose one spot to make a double bond when we make a double bond, remember that we cannot just sort of draw a line. We're actually taking a pair of electrons and sort of moving them in to make that double bond. So essentially, we need to erase a pair of dots and replace it with a line. And that may solve your problem. It may get everybody to 8 electrons. If it doesn't, you may need to do another double bond if that's possible. And if that doesn't solve it, at that point, you may need to go to a triple bond. Triple bond works the same way. Again, we would be bringing in our pair of electrons to make that triple bond. And at that point, hopefully that should fix your problem. Now, oftentimes when people sort of draw Lewis structures, as we talked about, sometimes it's not best to sort of double bond or triple bond right out of the box. People oftentimes do want to do that. Again, sometimes that will lead to structures that are incorrect, the wrong number of electrons, too many bonds, and things like that. So if you follow those sort of rules that we just talked about and we did yesterday, you really should lead you to a fairly good Lewis structure. Now, speaking of fairly good Lewis structures, how do we know if, perhaps one Lewis structure is sort of better than another? And again, that gets to a place where we talk about, it is possible to maybe draw things different ways or connect things in different ways. And that led us to sort of a talk about formal charge. And formal charge is really a way that we could calculate sort of what the charge would be on an atom in a particular sort of covalently bonded compound. And to calculate formal charge, we do the number of valence electrons in the free element minus the number of non-bonding electrons minus 1/2 the number of bonding electrons. And this gives us our formal charge. And we can calculate the formal charge on every element that we have. This is where we left off last time. And we can actually use something like formal charge to help us decide in situations of, when we do draw different sort of Lewis structures, which one might be better, which one might be maybe not so good in terms of a Lewis structure. So the ideal sort of situation when you draw sort of a Lewis structure is to sort of minimize formal charge. And minimizing formal charge means, if you could hit something where you get all zeros in terms of the formal charge, that's probably the best arrangement for those atoms to come together in a Lewis structure. Small formal charges are best. Things with really large formal charges, +2s, +3s, +4s, whatever it may be, is probably less likely to be happening or occurring or lead to the best structure. Also, if we have a situation where we have sort of equal distribution of formal charge, we would want the more negative formal charge to end up on the more electronegative atom. And again, we can use these sort of rules to help us decide, based on formal charge, which picture might be better than another. And that's sort of where we finished up on here, looking at sort of this example here. This is 2 ways that we could maybe draw formaldehyde. And again, you may want to hook up, in the first case, one of the hydrogens to the oxygen, providing sort of 2 central atoms. Or you may want to hook both hydrogens to the carbon. And we saw when we went through sort of the formal charge there at the end, on the guy on the left, we ended up with zeros for the hydrogens, +1 for the oxygen, and -1 for the carbon. So not terribly high formal charges. But by moving that hydrogen to the carbon, we can see on the right-hand side, we pretty much have minimized all the formal charge there. And we ended up with basically zeros for every single element in that arrangement. And that tells us that really the best structure between those two really is the one on the right. So the idea behind bonding is to get everything sort of stable-ish, if you will, bring everything to a pretty stable sort of situation, and some things where we really don't have excess charge sort of moving around at different spots in a compound is a situation where we really have sort of minimized that and created a pretty good situation. So if we had to choose based on formal charge, which one would be sort of the correct structure, we would choose the one on the right, again, because of that minimized formal charge. Any questions on that stuff there? Okay, so why don't we do one more example here of sort of using formal charge to help us decide, you know, what structure is a better structure. So let's take a look at like CO2. So let's say we drew CO2 such as this. Let's say we decided I wanted to triple bond CO2 because, it looks much cooler with a triple bond, I think. All right, so between these two here, calculate the formal charge on each of the elements that are present and use that to help you determine which structure should be the better structure of the two. So take a couple of minutes and we'll talk about it. Okay, let's take a look. So we'll start over here on the left and see how we do. So we have a carbon, or the oxygen here, double bonded. So again, if we do the formal charge, it is the number of valence electrons in the free element, which would be 6 for oxygen, minus the number of non-bonding electrons, which is 4, minus 1/2 the number of bonding electrons. So remember, each line represents 2 electrons. So that is 4. That's going to give me 6 minus 4, which is 2, minus 1/2 of 4, which is also 2. That's going to give me a 0. So this double bonded oxygen is 0. The other double bonded oxygen will come out the same, which is 0 as well. And our carbon there in the middle is double bonded on each side. That would give me a formal charge that is 4 for carbon, which is the valence electrons, minus 0 as there's no dots on the carbon, minus 1/2 of there's 4 lines, which means there's 8 electrons there. That's basically 4 minus 4, which is 0. That's going to be probably pretty hard to beat here. So let's take a look at this side here. We got our single bonded oxygen. That is going to give us a 6 minus, in this case, 2, 4, and 6 non-bonding electrons, minus 1/2 of 2, which again is the 2 electrons in the line. That's going to be 6 minus 6, which is 0, minus 1/2 of 2, which is a -1. So this oxygen here carrying a -1 formal charge. Our triple bonded oxygen, don't see that too often. Formal charge is 6 minus 2 minus 1/2 of our 3 lines, which would be 6 electrons. It's going to be a 6 minus 2, which is 4, minus 1/2 of 6, which is 3. So that looks like it is a +1 happening here. And lastly, here we have our carbon that has a triple bond on one side, a single bond on the other side. Our formal charge would be 4 minus 0, as there's no dots, minus 1/2 of 8, since there are 4 lines, and that does give us a 0. So here we could see that for CO2, which is carbon dioxide, we do see that really this structure over here is obviously the better structure. All of the formal charge has been pretty much minimized to 0. Here, not terrible, but again, not as good as obviously this structure here. So that's why when we do see CO2, it is double bonded on both sides, not triple bonded. So again, it goes back to sometimes, students ask, why can't I just like triple bond out of the box or double bond out of the box or attach this element to this element rather than how it should perhaps be attached. And again, it has a lot to do with this formal charge, and the idea of bonding is to really sort of minimize everything, get everybody into a fairly stable state. And again, basically a 0 formal charge means, everything in terms of sort of electrons and everything is distributed fairly well in that particular molecule. Any questions on formal charge, and again, how to calculate it, how to use it to decide between two structures. A reminder, as I might have mentioned yesterday as well, you do not have to use formal charge to decide if you drew a good structure or not, unless the instructions tell you to do so. So, for example, if the instructions told you to draw two Lewis structures and pick one that is best based off of formal charge, then obviously you should do that. Or if you were given two Lewis structures and asked which one is the better one, you could use formal charge to do that. But you don't have to keep drawing Lewis structures and use formal charge to determine if what you drew is good or bad, unless obviously the instructions sort of tell you to do so. You do need to be able to calculate formal charge. So again, if you draw a Lewis structure, however you draw it, you do need to be able to calculate the formal charge, obviously, of every element that's present. Any questions on any of that there? Okay, then let us continue on here. We're going to talk about resonance structure. We talked a little bit about it, but before we actually officially sort of talk about resonance structure, we're going to talk a little bit about sort of bond length and bond strength and sort of relationship between those two things. This is a table of some bond length for some different bonds, and obviously you don't have to memorize any of these numbers that are on this table. But bond length is essentially the distance between two nuclei in a bonded atom. And when we do look at a chart such as this, we do see a sort of a pattern that occurs, especially when we're talking about sort of the length of a single bond versus a double bond versus a triple bond. And if we just look, for example, at the carbon-carbon bond and look at those three things, the carbon-carbon single bond, the carbon-carbon double bond, and the carbon-carbon triple bond. We see that the single bond is 154, the double bond is 133, and the triple bond is 120. If we look at the carbon-nitrogen single, double, and triple bond, we see a similar pattern. The single bond is 143, double bond is 138, and the triple bond is 116 in that particular case. What we're seeing in terms of bond length is when we start with a single bond, it is the longest. When we make a double bond, the distances between the nucleuses get closer. They kind of come in. And if we make a triple bond, again, they move themselves closer. So every time we sort of add a bond, if you will, everybody sort of brings themselves in. You could kind of think about it like how we were doing our Lewis structures there, where we would make a double bond or a triple bond, right? When we sort of make a double bond, a double bond or triple bond, we're kind of bringing those electrons in, right? And when it brings those electrons in, it is going to pull everybody kind of closer together. You got a lot more negative charge coming in here in this region, right? And remember that we do have positive charges at the nucleus, and it's just going to bring everybody kind of tighter into each other as we have a lot more negative guys being shared between the two atoms. Again, that opposite attraction between the nucleus of one atom and the nucleus of another to those electrons that are basically sort of housed between them, right? So kind of that area of sharing. And again, it's going to bring that nucleus on each side sort of in a little bit more. Again, the greater negative charge in the middle there, going to bring everybody in. So the typical trend that we do see is just that as we continue to sort of make bonds, we're basically bringing everybody closer and closer together. The distance between the atoms and the bond also get obviously closer and closer together. And we see that in with our carbon-carbon bonds. We also see that obviously with our carbon-nitrogen bonds on this list. Now, what we also see is, when we make a, say, double bond is not as twice as close as a single bond, and, it doesn't go sort of like that. Now, this does have a sort of direct relationship on sort of the strength of the bond. And what we see is in terms of bond strength, The triple bond is stronger than a double bond, and a double bond is stronger than a single bond. So a double bond is not like twice as strong as a single bond, or a triple bond is not like 3 times as strong as a single bond or anything like that. But what we do see is because of that sort of shortened distance as those atoms kind of come together as we continue to sort of add bonds, the strength of that bond becomes much stronger. So basically, single bond larger than a double bond, which is larger than a triple bond. And in terms of strength, a triple bond is stronger than a double bond, that's stronger than a single bond. I sort of relate it sometimes to like a pencil. If you grab like a brand new pencil, like right out of the box, you have no problem. You can take it and pretty much snap it. And two, with not a lot of effort, you could pretty much break that pencil pretty easy. Now, if you take that same pencil after you've taken some chemistry test and you have pretty much an eraser and like a nubbin of a pencil left, it's like that small. If you ever try to break a pencil that's super, super small, it's very, very hard to break. And it's sort of the same idea, when we talk about bonds, as we sort of bring everybody together, we are, in a sense, because we're talking about bonding, we are bringing those negatively charged guys now closer to the nucleuses of each of those guys, atoms that are in that bond, and it's going to be held a lot tighter, going to require a lot more energy, obviously, to break it apart. Any questions on that there? All right, so we talked a little bit about electronegativity earlier, and again, obviously, it plays a very big role in terms of helping us determine, is a bond going to be polar or non-polar? What degree of sharing is happening when we talk about a covalent bond? And remember that as we go up and to the right there, it is more electronegative, with fluorine being our most, and obviously down and to the left, our electronegativity decreases. And as we talked about before, again, when we get that sort of differences that occur from different parts of the periodic table, that's really where we get those ionic compounds. And again, that's because pretty much metals are in this area, non-metals are over here. So that really big difference creates that ionic bond that's happening, as opposed to when we're talking about covalent bonds, we're really just talking about sort of this area of the periodic table. Again, they're all very similar in terms of their electronegativity and also their periodic trends. We also talked about the idea of that diagonal relationship, right? That also occurs, that you can again get different elements that have the same sort of electronegativity, because one is further up on the periodic table and one is further to the left. So remember, though, that there is sort of a difference in terms of sort of polarity and what we're talking about here when we talk about electronegativity. When we talk about electronegativity, we're really talking about, as it says here on the top, and I mentioned earlier, what is referred to as bond polarity. And bond polarity is simply what we were talking about earlier, and sort of a review here, what we see on the screen is really only telling you that between those two atoms, for example, within a bond, is that bond going to be polar or non-polar? Will it share electrons equally? Will it not share electrons equally? And that's really what bond polarity and electronegativity is used for. It is used for and can be used for molecular polarity, which we'll talk about here in just a second, but only in a certain situation. And when we talk about molecular polarity in other situations, like we will talk about it in the next chapter, really more officially, there's other things that you do have to look at. But there are certain situations where both the bond polarity, talking about sort of the individual bond, will be the same as the molecular polarity. And it really has to do with, as we will see shortly here, diatomic molecules. And diatomic molecules, it is the same thing. When you have more than two atoms, though, it is definitely not the same thing. So again, our sort of difference here in terms of electronegativity values, as we saw the other day or yesterday, again, helps us decide sort of the difference, and also that relationship between percent ionic character there on the bottom and electronegativity difference. And again, sort of the relationship of how those guys sort of come together. Again, if we have sort of a 100% ionic character, we have a very big electronegativity difference. And obviously, a much smaller one, we have less in terms of percent ionic character. So we can use, again, these electronegativity values to help us decide. And again, these are just some examples like the ones we looked at, I think, the other day as well. Here with something like Cl2, obviously they have the same electronegativity value. They give you that difference of 0. And as I mentioned, sometimes when we talk about a electronegativity value of 0, it is sometimes referred to as a pure covalent bond. We will usually call it in here a nonpolar bond, which is the same thing. This is a nonpolar bond. Here with our HCl, like our HF sort of example that we used, again, the difference in electronegativity gives us that 0.9, which is above our 0.4 threshold, going to get that unequal sharing of electrons. Again, the electrons hanging out more on the chlorine than the hydrogen, creating a partially negative side to the chlorine in this bond, partially negative side, partially positive side on the hydrogen. Again, also could represent this with a dipole arrow here that looks something like this. Again, this arrow always points to the more negative side. The part of the arrow that kind of makes like a plus sign on the back end is to the more positive side of it. And then here, obviously, we have our ionic compound, which is above 2. And there was a question, I think, the other day as well, and we talked about it, that, that 2 cutoff is relative. It works in a lot of cases, but not 100% of the time. But again, this is where we can just look at it and remember that it is a metal and that is a non-metal. So really, that's pretty much all you need to make that ionic determination that's happening. Now, when we talk about sort of bond polarity, as I mentioned before, it is something that's different than what is referred to sometimes as molecular polarity. Now, when we're dealing with a certain type of sort of molecule, we can sort of determine molecular polarity by looking at that particular element. And that is because it is a diatomic molecule. So a diatomic molecule basically means, as we talked about, that basically there's just 2 elements, basically, or 2 atoms involved. Not 2 elements, but basically 2 atoms involved. And because there's only 2 atoms involved in a particular sort of compound, what that means is that this particular compound only has 1 bond. And because it only has 1 bond, the entire molecule also has only 1 bond. And if that 1 bond is polar, then the molecule will be polar. And obviously, if that 1 bond is nonpolar, then the molecule would be nonpolar. So this is really sort of the one place where we can apply both bond polarity and molecular polarity, that they really do sort of cross over, if you will. They really do basically tell us the same thing. And what I mean by that is, if something is deemed to be polar, it is what is sometimes referred to as having a dipole moment. And a dipole moment can be represented with that same type of arrow. And what that means is within that particular molecule, for example, there is a side of the molecule that is more positive, and there's a side of the molecule that's more negative as a result of unequal sharing of electrons that are happening. So when we look at some things, we can relate both bond polarity and molecular polarity will really be the same when we're dealing with diatomic molecules. When we're dealing with things that have more than two sort of atoms involved, there's a lot more things that you have to take into account, and we'll talk about that in the next chapter. But you can sort of look at bond polarity and molecular polarity as being the same when you are dealing with diatomic molecules. So here's an example of some dipole moments of several gas molecules. Cl2 has a dipole moment of 0, which means it's basically nonpolar. ClF has this difference in electronegativity of 1, HF, and so forth. So when we look at something like Cl2, and we do the change in electronegativity as we see from the table here, it is 0. And what we know about the change in electronegativity here is that this bond right here, that is a nonpolar bond. Now, if we wanted to make an assumption about the polarity of this entire molecule together, we can make a fairly safe assumption that because this one bond here is nonpolar, and it's the only bond that we see in this entire molecule, this molecule will also be a nonpolar molecule. And we could do that safely and be correct because, again, it only contains one bond. So if it only contains one bond and that bond is nonpolar, then the whole thing is going to be nonpolar. Just like when we look at HF that we saw earlier, when we looked at HF, we know that the difference in electronegativity, as we can see from this table here, 1.9, means that when we look at this bond here, it is a polar bond. And the same reasoning, because that's a diatomic molecule, when we look at something like HF as a whole, this guy would be a polar molecule. And this guy would be a polar molecule because the one and only bond that's present is a polar bond. So we know that this guy definitely is going to be a polar molecule as well. We could represent that polar molecule with that arrow, and this would have what is referred to as a dipole moment. Again, this arrow pointing to the fluorine, which means that the fluorine is more negative, and the part that makes like the plus sign, as we talked about, pointing to the hydrogen, which is more partially positive. And what that really means is, as we saw sort of in a previous picture, what it really means is when we look at this molecule of like HF, for example, if all my little lines are the electrons, a majority of all the electrons are pretty much hanging out over here by the fluorine. While when we have our H, not very much of electrons are hanging out on that side of sort of the bond. So we get this sort of overall in this particular molecule, because it's a polar molecule, we have unequal sharing of electrons, which creates that sort of negative side to this molecule by the fluorine, positive side by the hydrogen in this particular case. Any questions on that? And that is different than what we see here, obviously, in our nonpolar molecule. And I'll do my best to draw it, and it probably won't come out great. But in a nonpolar molecule, again, what we would sort of typically see is sort of an even distribution, if you will, of those electrons all around the molecule. And in a nonpolar molecule, just like in a nonpolar bond, there's sort of that equal distribution of electrons, which means it really doesn't create a side that's more positive or more negative in that sort of bond, or in this case, the molecule, because we have sort of an even distribution of those electrons we could kind of think of the molecule and the bond as well, if we're talking about a nonpolar bond, as being sort of neutral, if you will. There's not a positive side, there's not a negative side. And we only get that sort of positive side and negative side when we get something that is sort of polar in that case. So something that's polar, either a polar bond means one side of the bond is more positive, one side is more negative, and a polar molecule, as we'll talk a little bit about here right now, and more in the next chapter, in a polar molecule, there's one side of the entire molecule that's positive and one side that's more negative. Any questions on that? So it's a really important thing, again, to sort of keep in mind that, when we talk about polarity, we oftentimes talk about those two types of polarity. And like I said, we'll talk more about it, obviously, in a little bit more detail in the next chapter, really, where it's sort of molecular polarity is sort of the major topic. But bond polarity, when somebody talks about what is the bond polarity, we're really talking about specifically just between two atoms. Are those electrons going to be shared equally or non-equally? And what helps us determine that is really electronegativity. When we talk about molecular polarity, and again, when we talk about more in the next chapter, when we talk about molecular polarity, usually what we're talking about is the entire molecule as a whole, all the bonds that are involved, how are the electrons shared over the entire molecule. Again, the one and only place where that sort of crosses over between bond polarity and molecular polarity is in what we were just talking about there in the last example, in a diatomic molecule situation, because that molecule only has one bond. So it basically determines whether or not the entire thing is polar or non-polar. But definitely a lot of difference happens when we talk about three or more atoms involved. There's a lot more things you have to take into consideration when you're dealing with something that has three or more atoms in terms of molecular polarity. So obviously we've done some examples like this previously, but obviously if we wanted to know, is this nitrogen-oxygen bond ionic, covalent, or polar, or non-polar, we would look at our electronegativity values, our N and our O, 3 and 3.5. We would subtract them. That is 0.5. That means that's above 0.4, but less than 2. So it would be a polar bond. And remember, as we've talked about a number of times at this point, really you don't even actually need these values, because again, in this case, if you look at the periodic table, you got your carbon, your nitrogen, your oxygen, your fluorine, basically all sitting in the same period. And we could very easily see that oxygen is further to the right, which would make a very safe bet that oxygen is more electronegative, and the resulting bond between nitrogen and oxygen, even without the numbers, could probably safely be determined that it is going to be a polar bond, and oxygen would be more electronegative. So we would draw the arrow heading towards the oxygen, meaning that the oxygen would be more negative, partially negative, nitrogen being more positive in this particular case. So again, as I mentioned a number of times the other day as well, there's a lot of situations where you don't necessarily need, those actual values. And sometimes people get I don't want to say crazy, but a little nervous, like I need the values. But there's certain situations where you really don't need the values. You could really determine, pretty safely if it's polar or non-polar by the general trends. Any questions on a little bit about that polarity? Again, we're going to definitely get into molecular polarity in the next chapter after we talk about a couple of other things. So we're now going to talk about energy here, and probably the one place that we will talk a little bit about actually doing some energy calculations and such. And we're going to talk about bond energy, and bond energy is sometimes referred to as bond enthalpy. And we talked a little bit, I think, about enthalpy in an earlier chapter. Enthalpy is the one way that we sort of measure heat, if you will, or energy. And So delta H, remember, is the change in enthalpy. And we could use these sort of delta H values to help us determine whether or not something is going to be exothermic or endothermic. So when we talk about exothermic, that means that heat and energy is released. If the delta H is positive overall, that means it's endothermic. And heat and energy is absorbed. So overall, when we talk about sort of energy and bonds being formed, there is a certain amount of energy associated with the process of both making bonds and breaking bonds. So when we sort of make bonds, it is a exothermic process. So think about just logically when we want to make bonds, we basically need to have things sort of come together. So things have energy to begin with. So as they sort of lose energy, exothermic, they sort of slow down and they allow themselves to sort of come together. Happens just like that. Not really, but that's sort of what happens. Um, if we already have a bond, they're sort of bonded together, we actually have to put energy in there, which is endothermic. And as they gain energy, they get enough energy to kind of wiggle away from each other. So when we break bonds, it's sort of an endothermic process, sort of a positive process in terms of energy. When we make bonds, it's an exothermic process, sort of a negative process, if you will, releasing that energy when we do that. Now, the greater the number of bonds, the shorter and stronger the bond gets, as we just talked about. Again, that relationship between um, the length of the bond and the strength of the bond. So when we think about a double bond versus a triple bond, or a single bond versus a triple bond, we would expect, as we just talked about a second ago, that a triple bond is much stronger, which would require a lot more energy to be put in to break it, as opposed to a single bond would take a lot less energy, basically, to sort of break it. Now, we could calculate the change in enthalpy based on bond energy. So the delta H change in enthalpy based on bond is basically as we go from the reactant side or the starting material in a chemical reaction to the product side. There's a couple of things obviously you hopefully should know, right? We do not lose any elements along the way, right? We have sort of that conservation of elements as we go from our sort of starting material to our ending material. The only difference is how they are arranged, right? So as we go from reactants to products, we basically need to break all of the bonds that are over here, and we need to pretty much make all the new bonds that exist over there on the right-hand side. So when we calculate sort of the overall energy change that occurs as we go from, say, reactants to products in a chemical reaction, as we break all those bonds on the reactant side to all those bonds that are being made on the product side, there is a change in energy that occurs. And that is sometimes referred to as the delta H of bond energy or the bond enthalpy. And we basically could calculate it simply by adding up all the energy required to break all the bonds on this side. So to break all the bonds, plus all the energy required to make all the bonds on the product side. And when we do that sort of addition and add that all together, we get an overall reaction, our delta H value for the reaction, which tells us as a whole, is this reaction endothermic or exothermic? Is this reaction basically going to give off energy as a result of that? Or is it going to basically absorb energy as a result of that? So let's take a look at sort of how we could kind of go through this process and how we could calculate this. Let's move that there, I think. So here's a table of bond energy. It's not from your book, but you have a similar one in your book. And obviously this would be provided for you if you needed. And basically you could use a table such as this to help you determine, you know, what is the total amount of energy that's going to occur here when we have a chemical reaction and we go from reactants to products. So we do see obviously what we talked about. For example, we could just look right here: single bond of nitrogen, double bond of nitrogen, triple bond of nitrogen. Energy to break the single bond 163, energy to break the double bond 418, much more energy. Energy to break the triple bond 946. Again, as we keep adding those bonds, the distances between the nucleuses get smaller and shorter, which means they're going to be held a lot tighter and take a lot more energy to try to break that. So let's take a look at one here. We want to basically figure out what is the enthalpy change for this reaction, or the delta H of this reaction. And we basically could do that by looking at, this is our reactant side, this is our product side. And again, basically what we're going to have to do is break apart all of the bonds that are on our reactant side. And we need to put together basically all of the bonds that are on our product side. So sometimes in this particular case, obviously it is drawn for you, the Lewis structures. And sometimes it's a really good idea, especially in these type of problems, um, to draw the Lewis structure to make sure that if you're not sure what you're dealing with, you know what you are dealing with. And what I mean by that is, sure, you may look at the formula, it may say CH4, but you want to make sure, am I dealing with a carbon hydrogen bond that's a single bond? Is it a double bond? Is it a triple bond? So as we just saw with the nitrogen example, it makes a big difference in terms of the number if you're dealing with a double bond, single bond, or triple bond. So if you're not 100% sure of what it looks like or what bonds that you have in there, you then would want to make sure that you maybe quickly sketch the Lewis structure so that you sometimes can visually see all the bonds, that you don't miss bonds. It's very common. Sometimes people will miss bonds when they just look at sort of the chemical formulas and not the Lewis structures. So let's take a look here and see what we need to do. So basically, if we start with our CH4, which is methane, we are essentially going to be breaking one carbon hydrogen bond, two carbon hydrogen bonds, three carbon hydrogen bonds, and four carbon hydrogen bonds. So we're going to be breaking four carbon hydrogen single bonds. So again, we would go to our table, look up carbon hydrogen single bonds, and we see that it is 414 kilojoules for a carbon hydrogen single bond. So basically, we're going to take 4 times 414 kilojoules, the energy to break each of those bonds. When we come over here, we're also obviously going to be breaking one chlorine-chlorine bond here. And this is again one chlorine-chlorine single bond here. Again, we would go to our table and find chlorine-chlorine, which is here somewhere. Where are you at there? And it is right there, 243 right there, if I'm not mistaken. So we got our 243 happening there at our Cl-Cl bond. So one at 243 kilojoules. This takes care of all of our breaking that's occurring here. So we actually could add it up. So if we add it up, that is going to give us 4 times 414 plus 243, looks like. Actually hit 243. Looks like perhaps we have 18 99 kilojoules in this case. We are then on the other side going to be making, in this case, one carbon hydrogen bond, one carbon hydrogen bond, and one carbon hydrogen bond. So in terms of making, we are going to be making 3 of the carbon hydrogen bonds, single bonds. We know from the previous there that the carbon hydrogen single bond is 414 kilojoules. We also then will be making 1 carbon chlorine single bond. So carbon chlorine single bond. We would go back for our carbon chlorine single bond, which looks like it's on the bottom there at 339. So 1 at 339 kilojoules. And lastly, we have one more bond over here that we're making, which is 1 hydrogen chlorine bond. Again, we would come back here and find hydrogen chlorine. Looks like 431, I think there. My eyes are right. So 1 times 431 kilojoules. Again, basically just going to add those together. This is all the energy required to make our bonds. So that's 3 times 414 plus 339 plus 431. And that gives us, looks like 2012 kilojoules. First off, any questions on how I got any of those numbers there? Okay, so we just talked about the idea that when we break bonds, it is endothermic. And when we make bonds, it is exothermic. So when we break these bonds endothermic, which means all these numbers that we just did here would be positive. Making bonds would be exothermic, which means all these numbers technically here would be negative numbers, which means this guy would be negative. So now we're ready to calculate the delta H of this reaction. And we basically would take all of our breaking, which is 1899, again, positive. We'll put it here, don't need to, plus our negative 2012, which is what we have for making our bonds. And if we take basically 1899 minus 2012, that's going to give us a minus 113 kilojoules, which basically means that overall, this reaction is exothermic based on bond energy, which means there's sort of a net release of energy as a result of breaking the bonds and making the bonds in this particular case. Any questions on how we got those numbers or anything like that? And again, just sort of visually, I think that's what we got going on here. By the way, as well, that's sort of what they did in the background. You know, sometimes people will show this type of calculation like this. They'll go, well, you know, we broke on this side 4 carbon hydrogen bonds and we made 3 carbon hydrogen bonds. That's a net difference of only breaking 1 carbon hydrogen bond. So sometimes people do this calculation where on the left-hand side, they would do 1 carbon hydrogen bond sort of difference and not do it on the other side. So sometimes that does happen and it comes out the same way. Or if you don't want to get confused by that, just do every single bond, even though you technically didn't really break these 3 of these bonds because they were still made on the other side. They really do cancel each other out. So sometimes people will kind of do it that way as well. Now, that's what we see here, and this is why overall this reaction is a sort of exothermic reaction. These are our reactants, which are starting here in terms of energy. As we start to break all these bonds, the resulting products that are made ends up being lower in energy. And this is a classic sort of exothermic energy diagram. So usually in like an exothermic energy diagram, this is your reactants, this is your products, this is energy. And whenever you have your reactants higher in energy than your products, the only way for them to get down there is to give off energy. And that is obviously exothermic. And that's what we see here is the net difference between all the breaking and all the making gives us this net difference of energy where the products end up being lower in energy than where we started with, which indicates that it is exothermic. And we see that it was exothermic based on the negative value that we got for the answer, which was negative 113. All right, so why don't you try one here? We'll do this one. I'll leave this one up since it's a big picture of the chart. Why don't you figure out what is the delta H for H2 plus O2 making some peroxide? So why don't you take a second and see what you come up with in this case, and we'll see if we come up with the same answer, hopefully. So calculate the delta H of this reaction, the enthalpy of this reaction based on bond energy, and also determine, is this reaction based on bond energy, is it exothermic or endothermic as well? All right, so take a couple of minutes to see what you come up with. Okay, let's take a look here. And so if you're given sort of this here in a just sort of formula form, if you will, like I mentioned before, sometimes it's a good idea if you're not 100% sure to perhaps sketch out the Lewis structures really quick, just to make sure that you are looking for the right type of bond. So if we're not sure, we can just kind of go through the same steps we did before. So we obviously have H2, so that is 2 electrons, which means obviously that is going to give us H2 that looks like this. That's going to then be plus O2. O2 is basically 2 times 6, which is 12 electrons. So again, if we do our single bond as 2, 4, 6, 8, 10, 12, we see the oxygen on the left there is short. So we do need to make a double bond, bring that in, get rid of those. And now we know, hopefully, that in case you weren't sure, we are actually dealing with an oxygen that actually is a double bond. And again, that makes a big difference when you go to this chart. If you grab the oxygen single number versus the double bond number. So this is what I was speaking to earlier, that you want to make sure that you understand what bonds you're dealing with in terms of, are they single, double, or triple. And again, sometimes just drawing things out gives you a visual thing to look at and make sure that you don't miss any bonds along the way. Now, again, H2O2, you may be wondering what's going on with that. H2O2, again, is 2 for the hydrogens and 12 for the oxygens. That's 14. The arrangement of hydrogen peroxide is actually, I'll just go down this way. Oxygen's in the middle, hydrogen's on the outside. Again, doing our one bond to everybody is 2, 4, and 6. That gives us 8 more to go, and that would then go here 2, 4, 6, and 8. So this is really the structures that we're dealing with and what we want to think about in terms of coming to this table and grabbing the correct sort of bonds. First off, any questions on that there? Okay. So now that we got everything that we need in terms of sort of looking at it, we can do our same thing. We could start with what we are going to break. And obviously in this case, we're going to break one hydrogen-hydrogen single bond. So one hydrogen-hydrogen single bond, which is right there on top. So that is going to give us 436 kilojoules. We're also, now that we were sure this is a double bond, going to be breaking oxygen-oxygen double bond here. And our oxygen-oxygen double bond is right there at 498. So one oxygen-oxygen double bond at 498. And that is going to do it for all of our breakage. And if we add that together, that is 436 plus a 498. Gives us 934 kilojoules that needs to be put in there to break both of those bonds. Remember, when we break bonds, that is endothermic, which means that's going to be a positive 934. Any questions on those numbers there? Coming to our other one here, we are going to break one oxygen-hydrogen single bond there and one more over here. So that is going to be making, I'm sorry, not breaking, but making two hydrogen-oxygen single bonds. So we're going to look for hydrogen-oxygen, which is right here, and looks like it is 464. So 2 times 464 kilojoules. We are also, and this is sometimes why it's important to draw these things, we also have a single bond between oxygen and oxygen in the middle. And it's very, very common, especially when you have multiple sort of atoms bonded to each other, when people do these type of problems, is for some reason people always seem to forget like the guy in the middle there and that bond that's happening. They're very focused on sort of the outside ones because they see like, oh, there's like OH, so that's definitely what's happening. And you might not visualize that you have an actual bond between the two oxygens, which clearly you do. And that's a very common mistake that people make, especially when they're dealing with, for example, a lot of carbons and hydrogen type things like this. Yeah. Sometimes people, when they're dealing with, say, something like this, and they have the formula given to them, like C3H8, they go, okay, well, there's like definitely sort of all these hydrogen carbon bonds, but they forget all about the sort of the carbon bonds that happen. So sometimes, again, visually sort of drawing these things help you not miss any of those type of bonds. So in this particular case, we're going with this guy here. And that would then be a one oxygen-oxygen single bond that's in the middle. And we saw that somewhere a second ago, I think. Oxygen, where are we at there? Single bond, 142. So it's going to be 142 kilojoules. Again, we're going to add this together. So we're going to take 2 times 464 plus, what did I say there, 142. It's going to be a 1070 kilojoules in terms of making. Remember, making is exothermic, which means really this number is negative, and that number is negative, and this number should be negative as well. At this point, we pretty much just need to add these numbers together. That gives us our delta H of the reaction here would equal positive 934 kilojoules plus a negative 1070 kilojoules. So 934 minus a 1070, basically a minus 136 kilojoules. Again, negative value there telling us it is exothermic. So there's sort of a net release of energy in this reaction from all of the making and breaking of the bonds that are occurring. Any questions on how to do this type of calculation here? Obviously, the table would be provided for you if you needed it. Okay, and again, the best piece of advice you could give in terms of this type of calculation is, take a second. You don't have to perfectly draw all of the Lewis structures with all the non-bonding electrons, but the most important thing to try to sort of visualize is what are all the bonds that you have, and are they single, double, or triple? Yeah, to answer your question, if in the end, when we calculated, the question was, would it be endothermic if the value was positive? And the answer would be yes. So if you got to this point and you added together your numbers here, and this number ended up being a positive number, then it would indicate that it's endothermic in that particular case. And that would mean that in terms of that sort of energy diagram that we were looking at here, you would have sort of an opposite energy diagram, which is your reactants actually start lower in energy than your products. And it ends up at the end, the products are higher in energy. Only way to get there is to add energy in, which is endothermic. So there's sort of a net positive that occurs as you go in and as you go that way. You're welcome. How come the oxygen under making is a single bond? The oxygen under making is a single bond because this oxygen-oxygen bond that we're talking about is not the O2. It's not this guy. It's actually the oxygen that's in here. So it's this bond right here. And that bond right there in hydrogen peroxide is an oxygen-oxygen single bond. And again, that's what I was speaking to just a second ago, that sometimes people will miss that bond completely when they just look at the sort of chemical formula. And that's why I recommend that you kind of sketch out the Lewis structure so that you don't miss it. So this oxygen-oxygen here is the oxygen-oxygen bond that's in hydrogen peroxide, the H2O2. The oxygen-oxygen double bond that we have here is from the actual O2 or molecular oxygen molecule that we started with. This guy is from there. Other questions? Okay. Yeah, so it's very, very, like I said, it's very common for people to miss bonds, and it happens a lot with sometimes you're given a lot of organic bonds, organic molecules when you're doing these type of problems. And a lot of organic compounds, the connection that you see is like what I drew down here with this guy. Is like carbons attached to carbons attached to carbons. But sometimes people, when they just kind of look at the formula, go, okay, well, I definitely got carbons and hydrogens, so I got like 8, 1, 2, 3, 4, 5, 6, 7, 8 carbon hydrogen bonds, and forget all about sort of the other connections that are there. So again, sort of drawing them, sort of really important to allow you to do that. Yes. So technically speaking, you can do one of two things. You can kind of do it like, so the question is, when we multiply it by 2, I think was questioned, 2 times the 4, 64 here. It is technically negative. Technically, this number is negative because it's exothermic, this process, and the 142 is negative, which is how it becomes this. You could either change those to negatives when you're doing the multiplication part, or leave them positives and just make the grand total negative at the end, either way. But the overall process of making should be negative. And, you could do that just like I did there. Either you could change the individual values that you find from the table and make it, you could make technically any of these values negative from the table in the making process, or use them as positive values, but just make the overall answer negative for the making at the end, because that process is exothermic. Because when we talk about energy, and again, we don't talk too much about energy. This is probably it in terms of anything that involves energy and calculations. But when we talk about energy and sort of that idea of like an exothermic type process versus an endothermic process, when we do something that involves that, like say you're going one way is sort of exothermic, and like say you were doing something that was going the other way, that's endothermic, whatever it may be. Because there's a conservation of energy, what that really means is the amount of energy required to go, say, the exothermic way, we'll just call it 100, is the same amount of energy that's required to go the opposite way, really kind of undo it, if you will. But the only difference is the sign, and we represent the sign as being negative for exothermic and positive for endothermic, because we're putting energy in to do that. We're removing energy in the exothermic sort of process. So there's sort of a constant conservation of energy, which means when we talk about certain things, there's like a system, and there's basically everything outside of that's like the surroundings. And there's this perfect idea of exchange of energy, which means if something gives off energy, something else will basically gain the exact same amount of energy, but it's just sort of labeled differently in terms of its sign. So in this case, from my arrow, the system would be giving off the energy and be exothermic. So whatever amount of energy that the system lost, the system would lose, say, 100 kilojoules of energy, and it would be represented as negative 100 kilojoules of energy because it's being given off. The surroundings would then gain that 100 kilojoules of energy, and it would be noted as being positive because it's being absorbed. And I guess what I'm trying to say is you can see the number is exactly the same, just the sign is different to indicate sort of the flow of the energy, which way it's going, either being absorbed or being released by something. But there's sort of a way you can think of it as like a perfect exchange of energy, even though in reality probably not perfect, but there is sort of a perfect exchange of energy that's happening here. And that's sort of what we're talking about here. There's sort of a perfect exchange of energy that's happening, whether we are going to take the two oxygens and put them together or take the two oxygens and break them apart. The amount of energy required to do that numerically in terms of the number is the same. It just basically determines, the sign of it determines whether you're kind of putting that energy in or removing that energy. Other questions on that? Okay. So again, like I said, this is probably as deep as we will go into any type of sort of energy calculations and stuff like that. But it'll be in this relationship here in terms of bond enthalpy. So again, if you're talked about what is the energy based on bond energies, bond enthalpies they're sometimes called, this is sort of what we're talking about using a table such as this. Again, basically adding up all the bonds we break, all the bonds we make, and really the overall difference we have in terms of the energy associated with those guys. Okay. And they ended up with the same, so that's good. All right, so we talked a little bit about resonance structures the other day. We sort of jumped into it a little bit earlier when we were talking about carbonate, I believe. And again, remember, a resonance structure basically occurs when you have really more than one option, if you will. A lot of times for something like a double bond, you can deal with triple bonds as well, but usually double bonds is a lot of what you see with. And if you remember, say something like carbonate, which we'll see here in a second, again, we had options as to where we could place that double bond, where we could move those electrons in to sort of fix the problem and make the double bond. We could have double bonded up on top. could double bond to the left, to the right. And the reason we could do that is because there's more than one option. We could draw more than one Lewis structure. And when you have that option to do that, those are what are referred to as being resonance structures to each other. Again, represented by that two-headed arrow that we see on the screen. I think I drew the other day as well. And it's really because if you decided just to say double bond, say the carbonate to the top, it doesn't really adequately sort of describe what is going on in this particular bonding scenario. As I talked about, the reason you can kind of do that is those double bond electrons are sort of delocalized or sort of moving around. And, you know, at any given point, for example, with carbonate, they may be up there at the top and making the double bond there, but they then could maybe move to the other side and make the double bond on that side. So when we have a situation like that, we can't draw one sort of Lewis structure that really adequately describes what is happening there. And because in the real situation, the correct structure is probably somewhere between, say, all three of the resonance structures, two of the resonance structures, or something like that. Again, as we talked about the other day, you don't necessarily have to draw all the resonance structures unless you're asked to do so. You can just draw one resonance structure and be fine, or one of the structures and just be fine. For example, this is ozone, and ozone here, we could have double bonded on the left-hand side. We also could have double bonded on the right-hand side. And again, those are resonance structures of each other. You would not necessarily have to draw both of them if you weren't asked to do so. If you were just asked to draw the Lewis structure for ozone, if you drew the guy on the left, it would be sufficient. If you drew the guy on the right, it would be sufficient. And if you're wondering why there's charges here, these are the formal charges that we calculated earlier on in this guy. You could also obviously just draw it without the formal charges present. And obviously it would look something like this. Or again, double bonding on the other side will look something like this. So again, these are some resonance structures. Our carbonate that we saw as well, another good example of that. And again, these are also the formal charges that we calculated earlier on it. But again, we could double bond up on top. We could double bond on the left or on the right. This is also why we have the formal charges here, why we didn't draw it like with the bracket. Without the bracket, there's no charges written on the inside, so we just put it on the outside. So the reason we don't have brackets because we actually included the formal charges on the actual molecule. But you could do that. And again, as we talked about, it's basically because those double bond electrons, you know, they're kind of at some point over there. Maybe they're at top. Maybe they're moving this way. So they're sort of moving around. The correct structure is somewhere in between all that. The benzene ring is another one. It's more of an organic compound that you see when you take organic. It looks something like this. These are all carbons. So everywhere, that's a carbon, 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 that's a carbon. And there's basically a hydrogen at each of these spots. You could also move that three double bonds to the other side and draw a resonance structure like this. Sometimes in organic, they shorthand that whole thing and they'll bad ring. Want to try that again? They'll sometimes draw this circle to indicate that those double bond electrons in the center are basically delocalized and moving around at any given point in time. So a reminder again, it usually does happen when we have more than one option to make the double bond. But again, you don't necessarily have to draw all the resonance structures unless you're instructed to do so. Any questions on that there? All right, I think that's a good place. We will lay it up right there for today. And we will talk about experiment 6. A reminder that we will be having the exam on Monday, covering chapters 1, 2, and again from chapter 3, the only thing that you need to know is what electronegativity is and the general trend. in terms of electronegativity. You don't have to do any of the sort of electronegativity calculations or stuff like that that we did in this chapter. That will be saved for the next exam. We will have, I think what we're going to do is we're going to do a short lecture during lecture time, and we will take the exam at the start of the lab. So I think that's what we're going to do on Monday. We will take the exam at the start of the lab. It will be 2 parts. One part will be multiple choice, where you do not have to show work, just got to pick the right answer. And there will be a second part, which will be sort of written, where obviously you'll need to show work for anything that has work associated with it, and obviously show all your work and turn it in. We'll do it just like we did our quiz. Again, a reminder that you need to make sure that I could clearly see both you and your work area. I would say most all of you did a pretty good job of that, but just make sure that in case you didn't do such a great job of that for the exam, I need to clearly see what's going on. Any questions on that? A reminder as well, homework will be due on Monday. There will be a box for you to sort of turn it in. The answer is I do not know how many questions because it is not Monday morning yet and I haven't written it. Okay, maybe Sunday night I'll write it, but I haven't written it yet. So I don't really know right off the top of my head. Other questions? Okay. The homework will be due sometime on Monday. Yeah. So I don't know about 1 o'clock, but it'll be due sometime Monday. Usually I give you the whole day to turn it in. So sometime Monday before it's over, it'll be due. But the box for you to turn it in will probably appear somewhere around Monday for you to turn it in.